Good morning. In today's talk, we want to think about quantifying the amount of solute that we have in our solution. So last time we talked very qualitatively about solutions and different properties of solutions and how they're affected by temperature or pressure if we're dissolving a gas. But our focus today is going to be on how do we quantify how much solute is dissolved in our solvent. So there are several ways that we can do this in terms of the units, right? These are all different forms of what we call concentration. So we're going to talk about two of these today. We're going to talk about mass percent and something called molarity. We'll define later. So let's start with mass percent. So mass percent is simply the number of grams of solute, so it's mass or grams of solute, per 100 grams of solution. So it's often what we call a mass per mass unit. So it's the mass of solute, in this case over 100 grams of solution. And that's where the percent idea comes in, right? Percents are based on 100. 100. So for example, if something is 14% by mass, what that means is that it's 14 grams of solute per every 100 grams of solution. So that would be a 14 mass percent solution. So to calculate the mass percent, we simply need to divide the mass of the solute by the mass of the solution, right? Assuming they're both in, grams. And then multiply by 100% to put it in terms of a percentage. So here's this equation we can represent. So our mass percent will be our mass of solute over the mass of solution, remembering that the mass of solution, right, is the mass of the solute plus the mass of the solvent, right? Masses are additive. So if we know the mass of the solute and the mass of the solvent, we can add those two together to get to the mass of the solution. Now, while we'll focus on mass percent, there are some other related concentration units that you may be familiar with that are similar to mass percent. And so in these are things like parts per million or ppms and parts per billion. And these are the same kind of mass per mass unit, but instead of being out of 100 grams, they're out of a much larger number. They're either out of 1,000,000 grams or out of 1,000,000,000 grams. And so, for example, parts per million would be the number of grams of solute per 1,000,000 grams of solution. And these are usually used for things where we have a very low concentration, right? So very low amounts of solute where maybe our percentage would be far less than 1%, but we can express it in parts per million or parts per billion and have sort of a number. So this is often used in like water quality, and we might say, in the water there's 10 parts per million of lead or 2 parts per million of arsenic or whatever. So it's used when there's very low concentrations. Now, one way that we do it, one type of problem is simply to calculate the mass percent. Say, okay, here's my grams of solvent and solute. What is my mass percent? Another way that we use mass percent is if we're given the mass percent, we can often use that to convert or to figure out either the mass of solute or the mass of solution, right? So the mass percent allows us as a convenient way to go back and forth between, if we know the mass percent and how much solution we have, then we can figure out how much mass of solute's in there, or vice versa. And so sometimes we're trying to find the mass percent. Sometimes we're using the mass percent combined with one of these other things to find the missing piece. So let's look at a couple problems. So our first problem here is to calculate the mass percent of a sucrose solution containing 11.3 grams of sucrose and 412.1 milliliters of water. Now, we're going to assume the density of this solution is 1 gram per milliliter. Now, what you'll see is that we'll often be using density in these calculations to convert between grams of something and volume of something, because if our solvent is a liquid, we'll often have measured that in some sort of volume units, but to calculate a mass percent, we need a mass of solvent. And so we have to use our density to make that conversion. Okay? So let's think about what we have here. So the first thing is, right, our mass percent, right, if we want to know what we need to have, right, that's going to equal our grams of sucrose divided by our grams of solution. And in the solution in this case, right, that's going to be sucrose plus water. So what do we know? Well, if we look at our problem, we know the grams of solute, right? So we have the sucrose, right? That's our 11.3 grams. We know the volume of water, right? So we can convert this to the mass of water using the density, right? So let's go ahead and do our math here. So let's first convert our volume of water into mass. So we're going to take our 412.1 milliliters of water, and our density, right, is 1 gram, and I want the grams on top because that's what I'm trying to find, per 1 milliliter, right? Grams per milliliter. So I'm going to do my math now, and we're going to get a mass of, in this case, 412.1 grams, because we get the same number because we have 1 gram per 1 milliliter. Now, once we know this, now we have our grams of water. We can combine that with our grams of sucrose to get our grams of solution. And so my percent mass is going to equal my grams of sucrose divided by my grams of sucrose plus my grams of water. So I get 11.3 grams of sucrose over 423.4 grams of solution, and of course times 100%. So if I go ahead and do that math, I get 2.69% sucrose. So this solution comes out to be 2.69 mass percent sucrose. Okay, so there's a simple problem where we're just solving for the mass percent. Now, let's look at a second problem where they give us the mass percent, and so they say that this solution is 11.5% by mass sucrose, and they want to know how much sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5 mass percent. Assume the density of our solution is 1.4 grams per milliliter. So this should be the density of solution, not the density of water, is 1.04 grams per milliliter. So we're trying to find the mass of grams of sucrose. So if we think about our calculation, so remember and I'll just do it over here. Remember, our mass percent equals grams of solute, which is be my sucrose, over grams of solution times 100. So this is what I want to find right here. So that means my grams of sucrose are going to be my mass percent divided by 100 times my grams of solution. And that'll allow me to solve for my grams of sucrose. So what do I know? Well, I clearly know the mass of sucrose, so I know the mass percent. I know the volume of solution. So the soda is my solution. So I need to convert this into grams of solution. And I know the density. So again, this should be sort of a common theme. Right? We're going to maybe have to do a conversion. And so if I have 355 milliliters of soda, I'm going to want my 1 milliliter on the bottom, my 1.04 grams on the top. My milliliters will cancel, and I end up with 369.2 grams of soda, or solution. So now I'm ready to solve my problem. And so my mass of sucrose equals my mass percent, my 11.5% divided by 100 to put it back into the decimal, times my 369.2 grams of soda. And so if I carry that out, I'm going to get 42.5 grams of sucrose. So this can of soda contains 42.5 grams of sugar if it is 11.5 mass percent sugar. So, if we wanted to think about just writing this out the normal way, right? We did the math here, but 11.5%, right, sucrose is equivalent to our grams of sucrose, right, which we just got, divided by grams of solution times 100. And that's what, we converted here to solve for the grams of sucrose. We divided by 100 and we multiplied by my grams of solution, and that's how we were able to solve. So that's mass percent. So let's shift gears now and talk about our second type of concentration. And this is something called molarity. Now, as the name might imply, this is going to be a a moles-based unit of concentration, right? Molarity. And this is defined as the number of moles of solute per liter of solution, so volume of solution here. And molarity is abbreviated by capital M. So molarity, moles of solute over liters of solution. Now it's key that it's solution, not solvent, right? We need the volume of solution. Now, one sort of aside here before we think about the calculations, right, is because it is volume of solution, not volume of solvent, if we want to make a solution to a specified molarity, so we want to actually mix it up, you're going to add this specified amount of solute, how many moles of solute you need, we're going to convert that into grams, and we're going to weigh that out and add that. And then to the flask, we're going to add the solvent, assuming water here, till we get to the desired volume. So notice our goal here is to get to a certain volume, not to add a certain amount of water. So we don't say that we add 1 liter of water or some volume of water. We add until the desired volume of solution. So if we want 1 liter, we're going to add as much water as we need to get to 1 liter. If we want 2 liters, etc. Now the reason for that is the solute will take up a small amount of volume. So if I just went ahead and added 1 liter, let's say, then I would make over 1 liter of solution, slightly. So I need to add enough to get me to 1 liter. So maybe that's 98 milliliters, and that would get me up to 1 liter. So that's the key. We have a target volume of solution here. So let's just do a calculation to calculate the molarity. So let's say we're given a problem that says, calculate the molarity of a solution made by putting 15.5 grams of sodium chloride into a beaker and adding water to make 1.5 liters of solution. So let's remind ourselves that the molarity equals moles of solute, so in this case moles of sodium chloride, divided by liters of solution. So in this case, right, what do we know? Well, we know the liters of solution, right? That's 1.5 liters. Now, what we don't know is the moles of sodium chloride. So something we'll often find in these problems is that we'll be given an amount in mass and we'll need to convert it into moles. So again, we have to go back to what we've learned previously on how to convert between grams and moles and do that conversion. So let's do that now. So we have 15.5 grams of sodium chloride, and the molar mass of sodium chloride, right, is going to be 58.45 grams per every 1 mole. So notice we have grams on bottom here, so it cancels out. Now, just to remind you, the way we got to this was to take the mass of sodium, okay, and the mass of chlorine off the periodic table and add them together. And that's where we got to this 58.45. So if I do this calculation, I'm going to get 0.265 moles of sodium chloride. So now we have what we need to calculate the molarity. We have 0.265 moles of sodium chloride divided by the liters of solution, 1.5 liters of solution. So that's going to give me 0.177, and we use the capital M. So we have a solution that is 0.177 molar sodium chloride. Now, as we get used to this, right, it's important to understand what that means, right? So if I say it's 0.177 molar, what that means is I have 0.177 moles of sodium chloride in every 1 liter of solution. So molarity provides a nice conversion between how much volume of solution and how many moles of solute it contains. So I know that this solution is going to contain 0.177 moles in every liter. So, for example, if I have 2 liters of solution, right, it would contain twice this many moles. If I had half a liter, it would contain half of this many moles. So we can use this molarity as a way to convert between moles of our solute, how much we have, and the volume of solution that it's going to be in. So calculating molarity. So just like we saw with mass percent and how I just kind of alluded to, molarity is often used as a conversion factor. So let's say we have a problem that says how many liters, so we're trying to get to liters here, how many liters of a 0.225 molar calcium chloride solution will contain 55.8 grams of calcium chloride. So if we think about our basic definition, that molarity is going to equal moles of, in this case, calcium chloride over liters of solution. What are we trying to find? Well, we're trying to find the volume of solution, or the liters of solution. So we're going to use the molarity and the moles to calculate liters. So let's think about rearranging this equation a little bit. So how do we get the liters of solution by itself? So one easy thing to do is simply to bring this over here, right, or multiply by both sides so that I get the liters of solution times the molarity equals the moles of calcium chloride. And then I can get the liters by itself. The liters of solution equals the moles of calcium chloride divided by the molarity. So I can divide both sides by molarity. It cancels out over here, and we end up with our formula that we can solve for the volume of solution. So the volume of solution will be moles divided by molarity. So what do I know? Well, again, I know the grams, not the moles, so I'm going to have to do that conversion. And I know the molarity. So I got this one, right? So I'm all good there. But I have to get to my moles. So again, we're going to start with my 55.8 grams of calcium chloride. And I'm going to use my molar mass. So for every 1 mole, I have 110.98 grams of calcium chloride. So just simply by adding up the 2 chlorines and the calcium there, my grams cancel, and I do my math, and I end up with 0.503 moles of calcium chloride. So now I have my moles. So again, I can go through this idea here, and I know my liters of solution are going to equal my moles, 0.503 moles of calcium chloride divided by the molarity, which is 0.225. Molarity, remember molarity is moles divided by liters. And so if we think about it here, my moles cancel. So liters are going to be the unit that I have. And so if I do this math, I get 1.97 liters of solution is how much I would need. So in order to have 0.503 moles, I would need almost 2 liters of this solution that is 0.225 moles per liter, which makes sense, right? So if every liter of this solution contains 0.225 moles, if I wanted to have twice this much, right, then I would need 255. I can't. Here, let's go back here a second. I think I made a mistake in my calculation here. I punched the wrong number into my calculator when I was doing this. So let's go. Let me just rewrite this here. So we have 0.225. I think I punched 0.255 into my calculator. So let's try this again. So 0.503 divided by 0.225 equals 2.24 liters of solution. So, using molarity as a way to convert, in this case, from how many grams of solute we have to the volume of solution that it would be in. So these are a couple problems that we can do using molarity. Now, one last thing in this little unit that I want to talk about, and that is the ion. So one thing to keep in mind is that when we dissolve ionic material, so when we did mass percent, we looked for sucrose solutions, right? And so when you dissolve sucrose, it simply breaks down into small chunks of sucrose molecules that are invisible, right? So, but remember, when we dissolve ionic compounds, they break down into ions. So this calcium chloride, when it dissolves, it's going to make a calcium 2+ ions, aqueous, and 2 Cl- ions, aqueous. So we're going to dissolve and we're going to get these 3 ions in solution, right? 1 calcium and 2 chlorides. If we did it for sodium chloride like in the last problem, we'd get 1 sodium, 1 chloride. So this is what's actually going to be swimming around in solution. Now, let's talk a little bit more about ion concentration. And I'm going to write those 2 equations up here. So I got sodium chloride, solid, calcium chloride, solid. This is going to break down into sodium ions and chloride ions. This is going to break down into calcium 2+ ions and 2 Cl- ions. Okay. Now, what we can think about here is calculating that ion concentration. So, if we think about that 1 molar glucose solution, right? It contains 1 mole of glucose per liter, right? Because, again, it doesn't break down into multiple pieces. And so we just have to think about 1 number, right? But if we're thinking about ionic compounds, we can think about the concentration of the solution, right, which is what we typically do. So the reported concentration containing ionic compound reflects the concentration of the solute before it was dissolved, right? So it's how many moles that you dissolve in the volume that you're dissolving it in. So a 1 molar calcium chloride solution contains 1 mole, right, of calcium chloride. Now what about the ions? Well, it has 1 mole. If we have 1 mole of this, when it breaks down, we're going to end up with 1 mole of calcium ions, but we're going to end up with 2 moles of chloride ions floating around. So we have 3 moles of ions that are generated from this 1 mole of compound. The same thing with the sodium chloride, right? 1 mole of sodium chloride will generate, in this case, 1 mole of sodium ions and 1 mole of chloride ions. And so we can apply this to any solution, right? The concentration of the individual ions present in the solution can be approximated from the overall concentration by looking at the coefficients. So if I were to go back to the problem that we just did, and I were to have 0.225 moles of compound of this, that's going to generate 0.225 moles of calcium ions and twice that. So 0.45 moles of chloride ions. So we can take, if we want to know the moles of ions, we can take the moles of compound that we added times the coefficient in front of that ion. So a little bit, something else just a little consider when we dissolve ionic compounds. Well, so that brings to an end our discussion about concentration specifically. Next time we'll pick up talking about some different aspects of solution.